we sit together with the slow questions of our world and the wider sky above it. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. Tonight, we drift north, far north, to a place where the ground itself is older than memory, and where the air, in some places, has been holding its breath since long before the first cities rose. Picture our blue planet from far above. From orbit, you can see the great curve of it, the soft white swirl of clouds, the deep blue of the oceans. But look toward the top. Look at the broad ring of land that wraps around the Arctic, Canada, Alaska, Greenland, Siberia, Northern Europe. A vast circle of pale earth and dark forest and tundra that stretches across the roof of the world. Much of that ground is not just cold, it is frozen, and it has been frozen in some places for tens of thousands of years. This frozen ground has a name: permafrost. It is soil and rock and old plants and ice, all locked together in a hard, silent layer beneath the surface. In some regions, it is only a few feet thick. In others, it reaches down for hundreds of feet. In parts of Siberia, scientists have measured permafrost more than a kilometer deep. A frozen world hidden just below the soft summer grass. And inside that frozen world, something quietly waits. Air, old air, tiny pockets of gas, sealed into the ice and the soil, trapped there long ago when the climate was different, and the great ice sheets still spread across the continents. Some of those bubbles may hold breath from the last ice age, from a time when mammoths still walked the plains and the seas were lower and the world was a stranger, colder place. This is where our mystery begins, because that frozen ground is now changing, slowly in some places, faster in others. The permafrost is warming. The ice within it is softening. And as it softens, the old air begins to escape, drifting up through the thawing soil, hissing quietly from the floors of shallow lakes, bubbling out of cracks that did not exist a generation ago. What is in that air? What did the world smell like when it was sealed away? What gases did it carry? What microbes? What whispers of a vanished climate? We have some answers. We have many more questions. And the deeper scientists look, the more open the question becomes. There are competing ideas about how quickly this thaw will unfold. Some researchers believe the change will be gradual, spread across centuries, giving the planet time to adjust. Others wonder if the thaw might happen in sudden surges, with whole stretches of ground collapsing in a single warm summer. Both possibilities remain on the table. The evidence is still being gathered, season by season, drill core by drill core. And then there is the cosmic side of the story. Because permafrost is not only an Earth mystery, it is a window into how frozen worlds behave anywhere in the universe. Mars has its own permafrost, locked beneath its red dust. The moons of the outer planets, places like Europa and Enceladus and Triton, are crusted in ancient ice that may hide oceans below. What we learn from our own frozen north could help us read those other worlds. The questions are connected, even across the dark distance between planets. So tonight, we will wander slowly through this strange, quiet topic. We will look at what permafrost actually is, and how the old air came to be trapped inside it. We will hear about the craters that have begun opening in the Siberian tundra, sometimes with a sound like a distant drum. We will sit with the mystery of microbes that may have slept for 40,000 years, and the mammoth tusks emerging, pale and curved, from the softening cliffs along Arctic rivers. We will not solve the mystery. Nobody can, not yet. The science is still being written. The drilling rigs are still turning. The satellites are still listening. What we can do is wonder gently while you rest. Wonder about the deep silence of a frozen world. Wonder about the air it holds. Wonder about what it might be like to stand on that pale tundra at dusk, in a wind that smells faintly of something very, very old. Settle in. Let your shoulders soften. We have a long, slow night ahead, and the frozen ground is waiting to share a few of its secrets. Let us begin with the simplest question of all. What is permafrost? The word itself is a quiet little riddle made of two parts. Perma, meaning lasting. Frost, meaning frozen. So permafrost is ground that stays frozen, not for a season, not for a winter, but for years on end. The official definition, used by scientists who study the cold places of the world, is ground that has stayed below freezing for at least 2 years in a row. Most of the permafrost we are talking about tonight has been frozen for far longer than that. Some of it has been frozen for thousands of years. Some of it, in the deepest layers, may have been frozen for hundreds of thousands of years. It is important to picture this clearly. Permafrost is not a sheet of ice on the surface. It is not a glacier. It is the soil itself, the dirt and clay and sand and gravel, bound together by ice the way mortar binds together bricks. If you could dig down through a typical patch of northern tundra, you would first pass through a thin top layer that thaws every summer and refreezes every winter. Scientists call this top layer the active layer. It is usually only a few inches to a few feet deep. Below that is the true permafrost, hard as stone, cold as a freezer, sometimes shot through with veins of pure ice that glitter in the lamplight when researchers cut into it. The scale of this frozen world is hard to hold in the mind. Permafrost covers roughly a quarter of all the land in the northern hemisphere. Think of that. 1 out of every 4 steps you could take across the top half of the globe would be a step onto frozen ground. It stretches across most of Alaska, across the northern reaches of Canada, across Greenland, across vast swaths of Russia and Siberia, across parts of Scandinavia, and high up in the mountains of Central Asia. There are also smaller patches in the southern hemisphere, in the Andes, in parts of Antarctica, and on a few cold mountaintops. In some places, the permafrost is shallow, just a few yards deep. In other places, it is astonishingly thick. In parts of northern Siberia, the frozen layer reaches down more than 1,000 meters. To picture that, imagine 3 Eiffel Towers stacked one on top of the other, then turned upside down and pressed straight into the earth. That is how deep the ice and frozen soil go in some regions. 3 Eiffel Towers of darkness and cold, all of it locked in place by the slow patience of the last ice age, the age of the deepest permafrost, is something worth sitting with for a moment. The youngest layers near the top may be only a few thousand years old, but the deeper you go, the older it gets. Some of the thickest deposits in Siberia formed during the last great glacial period, which ended about 11,000 years ago. Other layers in undisturbed pockets may be far older still. When researchers pull up a core of this ancient ground, they are touching dirt that has not felt sunlight or warmth since before the first human cities were built. Before farming, before writing, before the wheel, what is inside this frozen ground is part of what makes it so interesting. It is not just dirt and ice. It is a kind of museum. Locked into the soil are tiny pockets of trapped air. Old plant matter that never finished rotting. The bones of animals that lived in the Ice Age. Seeds, pollen, microbes paused in midlife, their tiny cellular machinery slowed almost to nothing by the cold. There are even, in some places, whole mammoths, preserved well enough that their stomachs still contain the last meals they ever ate. A simple way to think of permafrost is this. It is a freezer the size of a continent. And like any freezer, it preserves what falls into it. The leaves that drifted down 10,000 years ago. The breath of animals long gone. The air of a world that no human ever saw. As long as the freezer stays cold, all of that stays where it is, silent and waiting. That is the basic picture. Frozen soil, a quarter of the northern lands, sometimes 1,000 meters deep, sometimes older than civilization, holding within it the quiet leftovers of a vanished world. In the sections to come, we will look more closely at what those leftovers are, and at the open question of what happens to them now that the great freezer is very slowly beginning to warm. To understand how the permafrost came to hold pockets of ancient air, we have to slow down and think about how the ground itself remembers. The story does not begin with soil. It begins with snow. Long ago, in colder times, snow fell on the high latitudes year after year and never fully melted. Each new layer pressed down on the one beneath it. Over centuries, that pressure squeezed the snow into ice. And as the ice formed, something quiet and remarkable happened. Tiny pockets of air got caught between the grains and sealed inside. Those pockets are bubbles. Each one is a small breath of the sky from the day it was buried. The air inside has not mixed with the air above for a very long time. It carries the same gases that drifted around the world when it was first trapped: carbon dioxide, methane, nitrogen, oxygen, even traces of dust and pollen from forests that no longer exist. When researchers drill into old ice, they are not just pulling up frozen water. They are pulling up samples of an ancient atmosphere. Permafrost works in a slightly different way, but the principle is similar. Permafrost is ground that stays frozen for at least 2 years in a row, and in many places it has stayed frozen for tens of thousands of years. It formed during long, cold stretches when the air above it rarely warmed enough to thaw the soil. As plants died and animals decayed, their remains got pressed into the frozen earth. Water seeped in and froze. Air got trapped between soil grains, inside frozen pores, and within the bodies of buried plants. Layer by layer, the ground became a kind of archive. The conditions had to be just right for this to happen. The climate needed to be cold enough that summer warmth could not reach far below the surface. The land needed to be flat or gently sloped, so soil and dust could pile up slowly without sliding away. Rivers had to flood in spring and lay down fresh sediment. Wind had to carry fine grains from distant places and drop them across the tundra. Each of these small, slow events added another thin page to the record. In some regions of Siberia, Alaska, and northern Canada, this process went on for hundreds of thousands of years. The frozen ground grew thicker and deeper. In places, it reaches more than 1,000 meters down. Within that depth lies a slow archive of changing skies. Near the top, the air bubbles are younger, perhaps only a few thousand years old. Deeper down, the air may date back to the last ice age, or even further. Researchers can sometimes match a layer of frozen soil to a known cold period by the kind of pollen or insect remains preserved inside it. How exactly the air got trapped is still partly an open question. In glacier ice, the path is clearer because snow turns to firn and then to solid ice in a well-studied sequence. In permafrost, the process is messier. Some air may have been pulled in by freezing water as it expanded. Some may have been pushed out as ice formed and then sealed in nearby pockets. Some may have arrived through the slow breath of microbes living deep in the soil, releasing gases that then became locked in place when the ground refroze. Researchers continue to debate which of these pathways matters most, and the answer probably differs from one region to another. What we do know is that this ancient air is not evenly mixed. Some layers hold mostly the gases of the original atmosphere, frozen in place from the world above. Other layers hold gases made by tiny living things that kept working slowly, even as the soil around them grew cold. These are different kinds of memory stored in the same ground. Telling them apart is one of the careful tasks of the people who study these cores. It is strange to think that the breath of an ice age morning still exists, sealed in dark soil far beneath the tundra. The wind that carried it has long since died. The animals that walked through it are bones now, or dust. The forests that exhaled into it have vanished or moved. And yet the air remains, held in stillness, waiting. When the ground finally warms enough to release it, that old breath will mix once again with the modern sky. What it will tell us and what it will change is still part of the open question this episode will gently turn over as the night grows quieter and the long story of the frozen world continues to unfold. To understand what the permafrost is holding, it helps to picture the long sleep it came from. The last ice age was not a single frozen moment. It was a slow chapter of the earth that lasted tens of thousands of years. During its coldest stretch, vast sheets of ice spread across the northern world. They covered land that is now city, forest, and farm. And beneath those sheets, and along their cold edges, the ground itself began to freeze deeper than it ever had before. The materials caught in that freezing were ordinary in some ways and astonishing in others. Plain water, of course, dust blown in on the wind, bits of plant matter that fell to the soil and never decayed, pollen grains so small you could not see them, tiny bubbles of the air that creatures of that time were breathing, and in some places, the bodies of animals that walked the cold plains, including mammoths, ancient horses, and bison, whose names we will never know. Each of these things is made of elements, and every element in the permafrost has a story far older than the ice age itself. The carbon locked in those frozen roots and leaves was once carbon dioxide in the sky. Before that, it drifted through the lungs of animals. Before that, it floated in oceans. And long before any of that, the carbon atoms themselves were forged inside ancient stars. Stars that lived, swelled, and died billions of years before the Earth even formed. The same is true for the iron in the blood of those buried animals. Iron is made deep inside massive stars in the final moments before they collapse. When such a star explodes, it scatters iron across space. Some of that iron drifted into the cloud that became our sun and planets. Some settled into the earth. Some traveled up through soil into plants, into the bodies of grazers, and into the bones now frozen under the tundra. The mammoth tusks emerging from the thawing ground carry atoms older than the sun. The water itself is a deeper mystery. There are several theories about how Earth came to have so much of it. One idea is that water arrived in icy comets, slowly delivered over millions of years from the outer solar system. Another is that much of the water was already here, locked into the dust and rock that built our young planet. A third possibility blends the two. The honest answer is that the question is still open. Some of the ice now melting in Siberia and Alaska may have begun its life far beyond Neptune, in a place colder and darker than anything our minds can hold. The gases trapped inside those tiny bubbles are made of even more familiar atoms: nitrogen, oxygen, a whisper of argon, a breath of carbon dioxide, a trace of methane. Each of these has its own ancient path. The oxygen we breathe today was made by tiny ocean creatures more than 2 billion years ago. They learned to use sunlight to split water, and they released oxygen as a gift no one had asked for. The bubbles in the permafrost still carry that gift, sealed since long before any human civilization began. Methane, too, is a kind of relic. It forms when microbes break down old plant matter in places without oxygen. Some of the methane in frozen soil is fresh, over the last few thousand years. But some of it may be much older, drifting up from deep layers where it has waited a very long time. Researchers are still working to tell these sources apart. The mix is complicated, and the chemistry does not always cooperate. What makes the permafrost so quietly remarkable is that it gathers all of these stories into one place: stardust, comet water, microbe oxygen, mammoth iron, ice age air. Every grain of frozen soil is a small archive of cosmic history, pressed together by cold and silence. The same atoms that drifted between galaxies are now stitched into the roots of grasses that died when the world looked nothing like it does now. We do not yet know how much of this archive will be readable once the ice is gone. Some of it will simply mix back into the modern air and vanish into the larger atmosphere. Some of it may be captured and studied before it escapes. The window for understanding is narrow, and it is closing at a pace no one can quite predict. For tonight, it is enough to picture that long sleep. A world of slow snow and patient cold, gathering atoms from across the universe and tucking them gently into the frozen ground. Beneath the tundra, the forces at work are quiet ones. There is no roar, no sudden shift, no visible drama. The thaw moves slowly, the way a held breath finally begins to release. To understand what is happening, it helps to picture the ground not as solid earth, but as a layered cake, frozen for thousands of years, with each layer holding its own old air, its own buried life, its own long silence. The first force is heat. Warmth from the air above seeps down through the soil, season by season. In summer, the top layer softens. This thin upper band is called the active layer. It thaws each year and freezes again when winter returns. Beneath it sits the true permafrost, ground that has stayed below freezing for at least 2 years in a row, and often for tens of thousands. For most of history, the active layer was shallow, and the deep ice stayed locked away. Now, in many places, the warm season reaches a little farther down each year. Heat is not the only force pressing on the frozen ground. Water plays a quiet role too. When summer rains fall on the tundra, they carry a small amount of warmth with them. The water sinks into cracks and pores, and it gives up that warmth to the ice below. A single rainstorm does not change much. But year after year, decade after decade, the rain becomes a kind of slow piston, pushing warmth deeper than the sun alone could send it. Pressure works on the permafrost as well. The weight of soil, snow, and ice presses down from above, while pockets of trapped gas press back from within. In some places, methane and carbon dioxide have been held under pressure for so long that the frozen ground above them acts like a sealed lid. When that lid begins to soften, the gases find new paths upward. The pressure does not explode outward in most cases. It simply leaks gently into the open air after a sleep that may have lasted longer than any written history. There is also the force of sunlight itself, reshaping the surface in subtle ways. Dark patches of exposed soil absorb more warmth than bright snow. Where the tundra loses its white cover earlier in spring, the ground heats faster, and the active layer grows deeper. This is one of the feedback loops researchers watch most carefully, though they still debate how strong it really is. Some studies suggest the effect is large and growing. Others find the picture more uneven, with some regions warming quickly and others holding steady. The full balance remains an open question. Wind shapes the thaw too, in ways that are easy to miss. In winter, strong winds can sweep snow off exposed ridges, leaving the soil bare to the cold. This actually helps the ground freeze deeper. In summer, the same winds can dry the surface, changing how heat moves through it. The interplay between wind, snow, and soil is part of why permafrost behaves so differently from one valley to the next. Two patches of tundra, only a few kilometers apart, can thaw at very different speeds, and researchers are still mapping out why. Gravity itself enters the story once the ground begins to soften. Frozen soil holds its shape because the ice between the grains acts like cement. When that ice melts, the grains lose their grip on one another. Slopes that stood firm for millennia can begin to slump. Hillsides slide in slow lobes. Flat ground develops shallow pits where ice once filled the spaces below. The earth in these places is quietly settling. The way a sleeper shifts under heavy blankets. There is one more force, harder to name, but real. It is time. The permafrost did not freeze in a single winter, and it will not thaw in a single summer. The cold that holds it in place was built up over tens of thousands of years, layer by layer, during long glacial ages. The warmth now reaching it is recent by comparison. How quickly the old cold gives way to the new warmth is one of the central questions in this field. Some models suggest a gradual softening that could stretch over centuries. Others suggest tipping points where the thaw speeds up suddenly once certain thresholds are crossed. No one yet knows which picture is closer to the truth. For tonight, it is enough to imagine these forces working together, almost in slow motion. Heat from above, water seeping down, pressure leaking out, sunlight shifting the surface, wind sculpting the snow, gravity easing the loosened soil. All of them moving with patience around a frozen world that is only beginning to wake. Picture a quiet lake in the far north on a still autumn morning. The water lies flat as glass. The sky above it is pale and soft. And then, very gently, a single bubble rises to the surface and breaks. A small ring spreads outward. Then another bubble. Then another. Across the whole lake, in slow, scattered places, the water keeps releasing tiny breaths from below. These are methane bubbles, and some of the gas inside them is very, very old. To picture the scale of what is happening, it helps to start small. A single bubble from one of these lakes might be no bigger than a marble. A few of them together would fit in the palm of your hand. On any given lake, on any given day, the bubbles look almost shy. You could sit on the shore for an hour and only notice a few. The sound, if there is any sound at all, is softer than a whisper. But these lakes are not rare. Across the top of the world, scientists have counted millions of them. They speckle the tundra in Alaska, in Canada, in Siberia, in northern Scandinavia. From the air, the land looks pocked with shining pennies. Some are no wider than a swimming pool. Others stretch for miles. If you placed every one of these northern lakes end to end, they would wrap around the planet many times over. Now imagine each of those millions of lakes releasing a few bubbles. a few more every hour, every day, every year. The marbles add up, the whispers add up, and the total amount of methane lifting out of the ground becomes very hard to picture in any everyday way. Researchers have tried. One common comparison is to think of a single thermokarst, like a lake formed when frozen ground thaws and sinks, as a slow, steady kitchen burner, a small flame, never roaring, just hissing along. Now multiply that quiet burner by the number of lakes across the Arctic. The image becomes a stove the size of a continent, all of its burners turned low, all of them lit at once. And that is only the methane we can see bubbling at the surface. Some of the gas dissolves into the water. Some seeps out through soggy soil. Some escapes in winter, when researchers have found bare patches in the ice where the bubbles never stop rising, even at 40 below. The age of this gas is the part that often surprises people when scientists capture the methane and measure the carbon inside. Some of the bubbles carry a chemical signature thousands of years old. A few carry signatures tens of thousands of years old. In some samples from Siberia, the carbon inside the bubble dates back to the last ice age. The breath leaving the lake this morning may be a breath that was first locked away when mammoths still walked the plains. Try to feel that for a moment. A bubble the size of a pea, drifting up through cold water, carrying carbon that has not touched the open sky in longer than all of recorded human history. Civilizations rose and fell, while that little pocket of gas waited in the frozen mud. And now, in a single soft pop on the surface of a quiet lake, it rejoins the air. How much of this is happening is one of the open questions in this field. Some studies suggest that thawing lakes already release a noticeable share of the methane coming from the Arctic. Other studies suggest the share is smaller, and that wetlands and other sources matter more. The measurements are hard. The lakes are remote. The bubbling is uneven. One spot on one lake might release more in a day than its neighbor releases in a month. There are competing pictures of what comes next, too. One idea holds that as the ground keeps warming, more lakes will form, deeper layers will thaw, and the bubbling will grow stronger over time. Another idea suggests that some lakes may drain away as the frozen walls that hold them give out, leaving dry basins that release their carbon in slower, different ways. Both pictures may turn out to be partly right. Neither is fully settled. What we can say is this: across the top of the world, on lakes most people will never see, a quiet exhale is underway. Old air, kept in long silence, is returning. The bubbles are small. The lakes are calm. The land looks much the same as it did a century ago, and yet the scale of it, added up across a frozen crown of the planet, may be larger than anyone yet knows. For now, the bubbles keep rising, and the question of how many and how fast drifts up with them. Picture yourself drifting above the far north, where the land stretches in slow, patient curves toward the horizon. From this height, the ground looks like a quilt stitched by something very old and very quiet. There are pale greens and rust browns, soft yellows where lichen crusts the rocks, and long ribbons of dark earth where the soil has turned over on itself. In summer, the top of this ground softens into a damp, spongy layer. Mosses grow there, and tiny flowers no larger than a fingernail. The colors are gentle. Nothing rushes. Now imagine you set your feet down on that soft surface. The ground feels strange. It gives a little, like walking on a thick wool blanket laid over stone. Beneath the green skin of moss and root, the soil is cool. Dig down a hand's depth, and you feel a chill that does not belong to the summer air. Dig a little deeper, and your fingers meet something hard. That is the frozen layer. That is where the long sleep begins. The soil locked in that frozen layer is not empty. It is full of carbon. Carbon is the building block of every leaf, every root, every blade of grass that ever grew here and then fell, year after year, for tens of thousands of years. In warmer places, fallen plants rot away quickly. Tiny creatures in the soil break them down, and the carbon returns to the air. In the far north, the cold slowed that breakdown to a crawl. Leaves and roots fell, were buried by new growth, and then froze before they could fully decay. Layer by layer, the cold pressed them down and held them still. If you could slice through the tundra like a cake, you would see this story written in the the soil. The top would be that bright, living mat of moss and tiny stems. Below that, a band of dark, damp earth, threaded with fine, pale roots. Below that, the colors shift, streaks of black and gray, and the faint yellow of old, half-frozen plant matter. Deeper still, the soil takes on a strange, marbled look, with veins of clear ice running through it. Some of those ice veins are as thin as a thread. Others are as wide as your arm. They glow a soft blue when the light catches them. Scientists who study these frozen soils believe they hold an enormous amount of carbon. Current estimates suggest the permafrost across the northern world contains roughly twice as much carbon as is currently in the air above us. The exact figure is still being measured, and the numbers shift as new cores are taken from new places. What is clear is that the amount is very large, and that no one has counted every grain of it. The question that sits under all of this is simple to ask and hard to answer. As the ground warms, how much of that buried carbon will return to the air, and how quickly? Some researchers think most of it will stay locked in the soil for a long time, because much of the carbon sits very deep and warms very slowly. Others suspect that even shallow thaw could wake the carbon faster than expected, especially where water gathers and microbes thrive. Both sides point to real measurements. Neither side claims the matter is settled. Stand quietly on the tundra, and you would not see any of this struggle. You would see the soft surface, the slow flowers, the gentle slope of the land toward a distant lake. You might see a few small mounds where the ground has heaved upward over many winters. You might see a shallow dip where the ground has settled, filled now with bright green grass. The carbon beneath your boots makes no sound. It does not announce itself. In some places, though, the soil tells on itself. A bank of earth along a river may show a dark, glossy face where the frozen ground has been cut open by flowing water. You can see the old plant matter pressed into layers, like pages in a closed book. You can smell something faint and earthy, the smell of plants that grew when the world was different. That smell is the carbon beginning to stir. How much of this hidden store will stay sleeping, and how much will rise back into the sky, is one of the great open questions of our time. The frozen ground holds an answer it has not yet given. For now, the surface stays soft, the flowers stay small, and the long quiet continues while the carbon waits in the dark and the cold, patient as it has always been. Deep inside the frozen ground, sealed away for thousands of years, there are tiny pockets of old air. Some are no bigger than the head of a pin. Others are large enough to see with the naked eye, trapped in ice like little glass beads. Each one holds a sample of the sky from a world that no longer exists. And when the ice softens, those pockets open, one by one, and the air slips out into our time. For scientists, this old air is something close to a message in a bottle. It carries the breath of a planet that was colder, drier, and quieter than ours. By catching it before it escapes, researchers can study the exact mix of gases that filled the sky long ago. They can measure how much carbon dioxide floated in the air during the deep cold. They can measure traces of methane, and sometimes even faint hints of dust and pollen that drifted on ancient winds. The basic method is simple in idea, though delicate in practice. A long, hollow drill bites slowly into the frozen ground. It pulls up a tall cylinder of ice or frozen soil, layer by layer. Each layer matches a moment in time, like the rings of a tree. Near the top sits the recent past. Far below sits an older world. By melting the ice in a sealed chamber, scientists release the trapped bubbles and gather their gases without losing a single breath. What that old air seems to say is remarkable, though parts of the story remain open. The carbon dioxide levels during the deep ice ages appear to have been much lower than today. The methane levels rose and fell in a steady rhythm, tied somehow to the slow tilt of the Earth and the spread of the great ice sheets. But the exact reasons for those rhythms are still debated. One theory points to the oceans soaking up more carbon when the world cooled. Another points to changes in the vast wetlands that swell and shrink with the seasons. Both ideas hold pieces of the truth, and the full picture has not yet come together. There is also a deeper question hidden in those bubbles. The air trapped in permafrost is not always the same as the air trapped in glacier ice. is soil, not pure water, and soil breathes. Microbes live in it. Tiny chemical reactions tick along, even at very cold temperatures. Some researchers wonder whether the air locked in frozen soil has changed slightly over time, altered by the slow, patient work of life. If that is true, then the message in the bottle may be partly rewritten. If it is not true, then the bottle holds a clean record. We do not yet know which is closer to the truth, and the question matters more than it sounds. Other clues hide in the old air as well. Different forms of the same gas, called isotopes, can be sorted out in the lab. Each form carries a faint signature of where it came from. Methane from a swamp looks slightly different from methane from a melting hillside. Carbon dioxide from a burning forest looks slightly different from carbon dioxide from the deep sea. By reading these signatures, scientists try to learn not just what was in the ancient sky, but where each puff of gas began its life. The readings are noisy, and the answers are partial, and the arguments among researchers go on. There is something quietly humbling about all of this. The permafrost is acting as a library, and the books are written in gas. Each bubble is a sentence. Each frozen layer is a chapter, and the librarians are racing the thaw, trying to read the chapters before the ice softens and the pages disperse into the wind. Some sections of this library are already gone. We will never know exactly what they said. Other sections still rest in the cold, waiting, untouched, since long before any human walked across the tundra. What the old air might tell us, in the end, is how the planet has answered big changes before. It might show us how quickly carbon can shift from Earth to sky and back again. It might show us how long it takes a cooled world to warm, or a warmed world to settle. The clues are real, but they are scattered, and they do not yet form a single clear story. Scientists are still piecing the fragments together, listening to the breath of the past as it leaks slowly from the ground. And somewhere in that breath, perhaps, is an answer we have not yet learned how to hear. Beneath the frozen ground, life has been waiting. Not the kind of life we usually picture, with leaves and limbs and warm blood. Smaller life, quieter life, tiny single cells sealed inside the cold, dark soil, holding still through ages we can barely imagine. Microbes, bacteria, archaea, fungi, and other things even smaller. Some of them slipped into the ice when woolly mammoths still walked the open plains. And now, as the permafrost softens, a few of them appear to be stirring. This is one of the strangest cycles in our living world. Most of nature pulses on rhythms we can see, day and night, tide in and tide out, summer warmth and winter sleep. But the microbes of the permafrost move on a far longer beat. They freeze, they wait, and then perhaps, after thousands of years, they wake. Their pulse is measured not in hours or seasons, but in entire ice ages. How they survive so long is still an open question. One idea is that these microbes enter a kind of deep rest, slowing their inner workings until they barely register as alive. In this slow state, they sip almost no energy and repair their cells just enough to hold themselves together. Another possibility is that some of them stay faintly active even at temperatures far below freezing, eating tiny scraps of carbon inside thin films of unfrozen water that cling to soil grains. Researchers have found hints of both. The full picture remains unclear. What seems certain is that life in frozen ground is far richer than anyone once believed. Old textbooks treated permafrost as nearly dead, a kind of biological vault. Newer studies suggest something different. A single gram of this ancient soil can hold billions of microbes, packed in such variety that scientists are still naming the species they find. Some of these tiny beings have no close living relatives in the warm world above. They are old branches of the family tree of life, branches that quietly kept growing in the dark. When the soil thaws, the rhythm changes. Water flows. Oxygen reaches places it has not touched in a very long time. The slow inner clock of these microbes seems to speed up. They begin to feed on the ancient carbon around them, the leaves and roots and animal remains that froze before they could rot. As they feed, they breathe out gases. Carbon dioxide where oxygen is plentiful, methane in the soggy, airless pockets below. This is the cycle that troubles many researchers. The microbes were once part of a slow loop in which carbon was buried, frozen, and held in place for tens of thousands of years. Now that loop may be opening into a faster one, where the same carbon is released back into the sky over decades rather than ages. How quickly this shift will happen and how much carbon will move remains one of the deepest open questions in climate science. There is also a quieter wonder here, separate from the worry. To imagine a tiny cell locked in ice since long before any city stood on Earth, slowly opening its inner machinery again, to picture it sensing warmth, sensing water, sensing the strange new chemistry of a world that has changed beyond recognition. We do not really know what such an awakening feels like from the inside, or whether feel is even the right word. The microbes do not think. They simply persist and then resume. Some of what wakes is gentle. Soil bacteria that help break down old plant matter, much like their cousins in any forest floor. Methane producers that have been part of wetlands for as long as wetlands have existed. Fungi that quietly digest ancient wood. These are familiar players, simply returning to familiar work after a long pause. Their cycle has been interrupted, not invented. Other things that wake are stranger. Viruses pulled from deep ice cores have, in a few careful experiments, shown signs of activity again after tens of thousands of years. Most of these target only amoebas, tiny creatures that drift in water. Whether older or more unusual microbes deep in the permafrost might also revive, and what they might do is still being studied. Some researchers think the risk to larger life is small. Others urge caution. The honest answer is that we are still learning the rules. For tonight, it is enough to picture the slow breath of the frozen earth, microbes drifting between sleep and waking on a rhythm measured in millennia. A cycle older than memory, turning once more beneath the soft northern light, while the rest of us settle into our own much shorter night. Frozen ground does not sit alone in the world. It touches rivers, forests, coastlines, and small towns. It shares its edges with lakes and bogs, with the roots of large trees, with the burrows of foxes and lemmings. And buried inside it, sleeping in the cold dark, are things that once shared the world with creatures long gone. Among the bubbles of old air and the dust of old plants, there are also old microbes, tiny living things that fell into the cold and stayed there. Most of these microbes are harmless. Many of them are simple bacteria that eat plant matter, the same kind that live in soil today. But some scientists have begun to wonder about the others. What about the germs that once made ancient animals sick? The viruses that lived in the lungs of a wolf, or the gut of a bison, or the warm body of a mammoth that died in the mud thousands of years ago. When the ground freezes around a body, it can preserve far more than bone. It can preserve, in tiny amounts, the things that lived inside that body too. The question is whether any of those things could still wake up. And here the science becomes careful and quiet, because we truly do not know. One line of research has shown that certain very old viruses can still be active. Working in the lab, researchers in France have pulled what are called giant viruses out of Siberian permafrost. These are large viruses that infect single-celled creatures called amoebas, not people. Some of those viruses were tens of thousands of years old. In the lab, in controlled dishes, they could still find their amoeba hosts and multiply. That result was surprising. It suggested that at least some viruses can survive a very long sleep in the cold. But the leap from an ancient amoeba virus to a danger for humans is a very large one. Most researchers say there is no good evidence that long frozen human diseases are waiting to come back. The germs that make us sick are usually fragile. They depend on warm bodies, on close contact, on the slow shaping of evolution alongside our own immune systems. A pathogen that last met a living host 10,000 years ago might not even recognize us. Our bodies have changed. The world around the germ has changed. Many old microbes, if they thawed today, would simply die in the open air. Still, the question lingers. Old graves do sometimes appear in the thawing ground. In the far north, there are burial sites from past centuries, including some from outbreaks of disease that swept through northern villages long ago. When the soil softens, those graves can shift. In one case, researchers traced a small outbreak of anthrax in Siberia to the thawing carcass of a reindeer that had died decades earlier. The bacteria that cause anthrax form tough spores, and those spores can wait in the ground for a very long time. Whether other diseases can do the same is one of the open questions that scientists are still trying to answer. There are competing views. Some researchers argue that the real risk from thawing permafrost is not ancient germs, but modern ones. As the ground softens, animals move into new places. People build new roads through land that used to be frozen solid. New contacts between species and between people and wildlife may matter far more than any sleeping microbe from the Ice Age. Other researchers say it is worth watching the old ground carefully anyway, simply because we have so little data. The deep layers of permafrost have not been studied in fine detail. We do not yet know everything that is down there. What seems clear is that the frozen soil is a kind of library of life. It holds the dust of plants that no longer grow, the cells of animals that no longer walk, and the smallest passengers those animals once carried. Some pages of that library will fade as soon as they touch the open air. Others may hold their shape for a little while longer. Which ones, and for how long, no one yet knows. For tonight, the picture is gentle and uncertain, a slow thaw across an enormous land. A few curious scientists in quiet labs, lifting a sample of dark earth and watching it under a lens. A question that has no clean answer, only a careful, patient listening. Somewhere under the tundra, in a layer of soil that has not seen the sun since before the first cities were built, something tiny is beginning to stir. What it is, and whether it matters, the world is still learning. In the far north of Siberia, the thawing ground gives up strange treasures. Tusks rise from the mud like pale, curved branches. Bones the size of a grown person appear in riverbanks where there were none the year before. And every so often, the soft soil reveals something even more astonishing. A whole animal, frozen for tens of thousands of years, still wearing its hair and skin. These are the woolly mammoths. They walked the cold steppes of the last ice age, alongside woolly rhinos, cave lions, and giant bison. They vanished from the mainland thousands of years ago. 4,000 years ago. That means mammoths still breathed the cold air, while the pyramids of Egypt were already standing. Now, as the permafrost softens, their remains are coming back into the light. Some are only bones. Others are far more complete. Hunters and scientists have found mammoth calves with their trunks still curled, their stomachs still holding the last meal of grass and flowers they ever ate. The cold did what no museum could. It preserved the soft tissue, the fur, even tiny details of the skin. The oldest mammoth remains pulled from this frozen earth are thought to be more than 50,000 years old. Some bones may be older still. They sit at the edge of what the science of dating can reach. When researchers cut into the tissue, they sometimes find blood-like fluid in the vessels. They find muscle that still looks red. They find a body that has waited in the dark and the cold since long before any human city existed. The numbers grow stranger the longer you look at them. In some parts of northern Russia, the ground is so full of Ice Age bones that local people have gathered mammoth ivory for generations. Whole rivers cut through banks of frozen silt where tusks stick out like roots. One small island in the Arctic, called Lyakovsky, has yielded so many tusks over the centuries that it became known as a kind of natural storehouse of the deep past. No one knows how many mammoths still lie hidden in the frozen north. The estimates run into the millions. Most will never be found. They rest in places too remote, too cold, too dangerous to reach. But the warming earth is changing that. Each summer, more of them slip from the thawing banks. Some tumble into rivers and are washed away before anyone sees them. Others are gathered carefully by scientists who race the season. The mystery is not only how many lie buried, it is also why so many died in the first place. The end of the Ice Age brought warmer temperatures, shifting plants, and rising seas. Around the same time, human hunters spread across the northern world. Some researchers think the climate change alone was enough to doom the great herds. Others think hunting pushed them past the point of recovery. A third group wonders if disease, or some mix of all three, did the final work. The debate is old, and it is far from settled. Even stranger questions sit just beneath the surface. When a mammoth comes out of the permafrost, with cells still recognizable under a microscope, some scientists wonder how much biological information might still be intact. Could fragments of ancient DNA, pieced together carefully, one day tell us how these animals lived, what they ate, what diseases they carried? A few researchers have asked even bolder questions about whether some version of the mammoth might be brought back into a living form. That idea remains highly contested, and many in the field consider it more dream than plan. For our quiet purposes tonight, the bones themselves are wonder enough. Picture them resting in the dim cold, layer upon layer, in a land where the sun barely rises for months at a time. Picture the soft hiss of a thawing bank in summer, the slow tilt of a tusk as the soil lets it go. Picture the patient work of scientists in heavy coats, brushing mud from a calf that last breathed when the great glaciers still covered half of Europe. The mammoths are not the only ancient creatures coming free. Horses, bison, and small predators have been found as well. Some so well preserved that their whiskers and eyelashes remain. The frozen ground has been a strange and gentle keeper of the past. As it softens, it is letting that past return piece by piece. What else lies waiting under the tundra, in the deeper layers? No one yet knows. The earth there is older than memory, and it has only begun to speak. Far to the north, across a wide stretch of Siberia, there is a kind of frozen ground that has its own name. Scientists call it Yedoma. The word comes from the Russian language, and it refers to a special type of permafrost found mostly in the eastern part of that vast country, and in parts of Alaska and the Yukon as well. Yedoma is not just frozen soil. It is something stranger and older, and many of its smaller details are quietly beautiful. Yedoma deposits formed during the last ice age, when the climate in this part of the world was cold and dry. Wind carried fine dust across the open plains, and that dust piled up over thousands of years. Mixed with the dust were plant remains, animal bones, and water that froze into ice. The result is a thick layer of ground that is more ice than dirt. In some places, Yedoma can be up to 150 feet deep, and as much as 80% of its mass is made of pure ice. The ice inside Yedoma takes a particular shape. It forms huge vertical wedges that reach down into the soil like long, narrow teeth. These are called ice wedges, and they grew over many winters, one tiny crack at a time. When the ground froze hard enough in deep cold, the surface would split. Water would seep into the crack in spring and freeze again. The next winter, the same crack would open and fill once more. Over thousands of years, those slow, repeating moments built ice wedges that can be 10 or 20 feet across at the top. If you could stand inside a Yedoma cliff and look closely, you might see fine layers running through the frozen wall. Each layer is a season. Each layer is a memory of a year long gone. Pale silts and darker bands of old plant matter stack on top of one another like the pages of a closed book. Some of the silt grains are so small they can only be seen through a microscope. They came from rocks ground to flour by ancient glaciers far away, then lifted by wind and carried for hundreds of miles. Within those silts, scientists find tiny treasures. There are seeds the size of a pinhead. There are pieces of grass blades, still green when first uncovered, then quickly fading in the open air. There are insect parts and small bones of mice and voles, and the shells of beetles that lived when mammoths still walked the land. Each fragment is a small clue to what the world looked like when this dust first settled. The air inside Yedoma is also full of detail. Tiny pockets of gas sit between the grains of soil and ice. These pockets hold the breath of the late Ice Age. Some of them hold methane, made by old microbes in the soil. Some of them hold carbon dioxide. When researchers carefully drill a sample and bring it to the surface, they can sometimes hear a faint hiss as the ancient air escapes. The sound is small. It is the sound of a world from long ago, letting go at last. What scientists still puzzle over is how much carbon Yedoma actually holds, and how quickly it might release it as the ground warms. One estimate suggests Yedoma soils may contain hundreds of billions of tons of organic carbon, but the true number remains uncertain. Some researchers think much of that carbon is locked away so deeply that it will thaw slowly over centuries. Others wonder if certain regions could thaw far faster because the ice wedges, once melted, leave behind hollows that collapse and expose more ground to the warm air. Both ideas have evidence behind them, and the question is still open. There are smaller mysteries too. Why is Yedoma so much richer in ice than other permafrost soils nearby? Why does it appear in some valleys and not in others? How exactly did the wind and cold combine in just the right way to build such deep deposits in this one part of the world? Researchers are still gathering clues from the layers and the bones and the dust. For now, Yedoma sits quietly across the Siberian plains and across parts of the Arctic in North America. Cliffs of it face the rivers, slowly shedding silt and ice into the slow brown water. Inside each cliff, there are fine grains, frozen seeds, and old bubbles of trapped air, waiting in the cold. They have waited a very long time already. The question of what they will tell us and how fast they will speak is still gently unfolding. In the summer of 2014, a helicopter pilot flying over the Yamal Peninsula in northern Siberia spotted something strange in the tundra below. A hole had appeared in the ground. Not a small hole. A vast, dark pit, almost perfectly round, with steep walls and a soft inner ring of crumbled earth. The pilot circled, took photographs, and brought the images back to scientists who had never seen anything quite like it. The crater was wide enough to drop a small house into, and no one could say with certainty how it had formed. In the years that followed, more of these craters were found. Some were spotted by herders, some by satellite, some by researchers who flew slow loops over the empty land, looking for changes in the texture of the soil. By the early 2020s, more than a dozen had been catalogued across Yamal and the nearby Jiden Peninsula. Each one looked similar. A round mouth, a deep shaft, a scattering of soil and ice flung outward, as if something had pushed up from below and burst through the surface. The discovery raised a question that geologists are still working to answer. What exactly had caused them? The leading idea is that pockets of gas, mostly methane, possibly mixed with carbon dioxide, had built up under pressure inside the frozen ground. As the surface thawed and weakened, the pressure found a way out, lifting a dome of earth and finally bursting through. In this view, the craters are like the slow opening of a sealed bottle that has been shaken for thousands of years, but the details remain contested. Some researchers think the gas comes from microbes feeding on ancient organic matter as the ground warms. Others suspect it rises from much deeper layers, from natural gas seeping up through cracks in the rock. A third possibility is that the gas was always trapped there, sealed inside lenses of ice formed during the last ice age, and that the warming surface simply opened the lid. These ideas are not mutually exclusive. The truth may be a mixture of all three. The science is young, and the field sites are remote. Before these craters appeared, the slow thaw of permafrost had been studied for over a century. Russian scientists in the 19th century had already noticed that the ground in Siberia stayed frozen far below the surface, even in summer. Engineers building railroads and mines learned, sometimes painfully, that the frozen earth behaved in unpredictable ways. It heaved, it cracked, it swallowed buildings when it softened. The word permafrost itself entered English in the 1940s, coined by an American geologist named Seaman Muller, who studied frozen ground for military engineering reports. For decades after that, the focus was practical. How to build roads on it, how to lay pipelines across it, how to keep foundations from sinking when the ice within the soil began to melt. The idea that the permafrost itself was an archive, a sealed library of ancient air, ancient microbes, ancient carbon, came later, and slowly it grew from the work of ice core researchers in Greenland and Antarctica, who showed that frozen layers could preserve gases for hundreds of thousands of years. If glacier ice could hold the breath of the past, then frozen tundra might hold it too. The craters changed the conversation. They made the invisible visible. A slow chemical process, hidden under meters of soil, suddenly had a face. People could stand at the edge of one of these pits and look down into a freshly opened wound in the walls, you could see the dark bands of frozen organic matter, the pale veins of ice, the layers laid down across thousands of years. The crater was a cross-section of time, exposed without warning. What scientists still cannot say is how common these events are, or how often they happened in the deep past. It is possible that the tundra has always released gas this way, slowly, quietly, in places no one was watching. It is also possible that the recent warming has made the process more frequent, and that the craters are a new feature of a changing world. Both ideas have supporters. Both lack the long record of observation needed to settle the question. For now, researchers map each new crater carefully. They lower instruments into the shafts. They measure the gas that rises from the walls. They listen for the soft hiss of escaping air. The frozen ground, which once seemed silent and still, is turning out to speak in ways no one expected. And much of what it is saying, we have not yet learned to understand. Most of us picture a thawing landscape as something silent, a slow softening of snow, a quiet darkening of soil. Yet people who live and work in the far north describe something stranger. The melting ground, it turns out, can be heard. It pops. It hisses. It sighs. It cracks open in the middle of the night with a sound like distant thunder rolling across the tundra. Researchers walking across thawing peatlands have recorded faint fizzing sounds rising from the moss. The noise comes from bubbles, tiny pockets of gas pushed up from below, breaking the thin film of water that coats the soil. Some of those bubbles carry air that has been sealed away since long before any city stood on Earth. When they burst, they make a soft sputter, like rain falling on a hot stone. A whole bog can whisper this way on a still afternoon. In winter, the sound changes. Lakes that hold methane underneath their ice can trap that gas in flat white disks, stacked like frozen plates. When the ice cracks under the cold, the disks shift, and the lake gives off a deep, almost musical pinging tone. People have stood on these lakes and heard the ice sing. The notes drift across the snow for kilometers, low and clean, almost too strange to believe. No one is certain why some lakes sing more loudly than others, or what controls the pitch. is another sound that catches travelers off guard. As permafrost loses its grip, the ground itself can groan. Frozen soil behaves a little like stone. When it warms, it twists and settles, and the ice inside it shifts. Hikers have reported a low creaking under their boots, almost like an old wooden floor. Sometimes a sharp crack will travel through the earth as a hidden lens of ice finally gives way. The land is rearranging itself slowly, and it is not quiet about it. Then there is the strangest surprise of all. In some thawing soils, the gas comes out so quickly that you can light it. Researchers have drilled small holes through lake ice in Alaska, held a match nearby, and watched a clean blue flame leap upward where ancient methane meets the winter air. The flame is brief and pale. The gas it burns may be thousands of years old, born from plants that died before the pyramids were built. To see flame rising from a frozen lake feels like something out of a dream. Yet, it has been filmed many times. Scientists are still trying to map how loud, how widespread, and how steady these sounds and seepages really are. Acoustic sensors have been buried in the soil to listen for the rhythm of bubble release. Microphones have been lowered under lake ice to catch the deep pinging tones. The early recordings hint at patterns, but the patterns shift from year to year. One theory holds that warmer summers produce noisier autumns, as more gas pushes upward through the softened ground. Another suggests the sounds depend more on the deep structure of the soil than on the surface temperature. The data is still thin, and the question remains open. There are other counterintuitive details. Thawing ground does not always sink evenly. Sometimes it bulges upward instead. Pockets of gas can lift the soil into rounded mounds called pingos and frost blisters. A few of these have been seen to swell over the course of a single season, like the slow breath of something underneath. Whether the gas inside them is fresh or ancient, and whether they tend to release their contents gently or all at once, is not fully understood. Even the color of the ground can change in ways that surprise people. Newly exposed permafrost is sometimes streaked with bands of gray, brown, and deep blue, depending on the minerals and the age of the ice. Veins of clear ice can shimmer like glass when the sun catches them. In some places, the soil smells faintly sweet or faintly sour as long-buried plant matter meets the air for the first time. The senses of anyone walking there are gently overwhelmed by a landscape that should not, by ordinary intuition, be doing any of these things. What all of this adds up to is a quiet truth. The thaw is not a silent process. It is a slow, layered performance of pops, hisses, groans, and faint blue flames. We are only beginning to listen carefully, and the recordings we have so far raise more questions than they answer. Somewhere under the moss, the old world is exhaling, and we have not yet learned the language of its voice. Far in the north, where the land meets the cold gray sea, something quiet and strange is happening. The coastlines themselves are slipping away. Whole stretches of frozen shore are crumbling into the water, year by year, season by season. In some places, the land retreats by many meters each summer. In a few spots along the Arctic, scientists have measured losses of more than 20 meters in a single warm season. The ground that held firm for thousands of years is now letting go. This slow undoing connects the permafrost to the wider world in ways we are only beginning to map. The frozen coast was never just dirt and ice. It was a wall, a long, curving wall of ancient soil, held together by frozen water like mortar between bricks. When that mortar softens, the bricks lose their grip. Waves that once broke against hard, cold cliffs now eat into soft, thawing earth. The sea takes a bite, and another, and another. What falls into the water is not ordinary sediment. It is old carbon, old air, old life. Soil that has not seen sunlight since the last ice age tumbles into the shallows. Bones of animals long gone slide down with it. Pockets of methane and carbon dioxide, sealed for tens of thousands of years, open into the salt water. Some of that gas dissolves into the sea. Some bubbles up into the sky. The exact balance between these two paths remains an open question, and researchers are still working to measure it. The sea itself plays a role in this unraveling. As Arctic ice cover shrinks in summer, more open water appears along the northern shores. open water lets the wind build larger waves. Larger waves carry more energy to the coast. The coast, now softer, gives way more easily. One change feeds the next, and the next feeds the one after that. It is a quiet conversation between ocean, air, and frozen ground. The sun joins this conversation too. Long Arctic summers bring weeks of constant daylight. That steady light warms the dark water where sea ice once reflected it away. The warmer water then washes against the frozen shore, thawing it from below, even as the air thaws it from above. The ground is sandwiched between two slow heat sources, and it cannot stay frozen forever under that pressure. Some researchers think this two-sided warming is the main driver of coastal collapse. Others suspect storms matter more. The full picture is still being assembled. When the coast falls, it carries pieces of history into the sea. Mammoth tusks have been found washed up on Arctic beaches, polished smooth by the surf. Layers of ancient plant matter drift into the shallows and feed strange blooms of microbes. Nutrients that were locked away for ages suddenly enter the food web. Fish, plankton, and seabirds may all feel the change in ways no one has fully traced. The ocean is gaining something old, and we do not yet know what that gift will do. There is also the matter of freshwater. As permafrost thaws inland, rivers run fuller and warmer. They carry sediment, carbon, and dissolved gases out to the Arctic Ocean. That fresh water forms a thin, cold layer on top of the salty sea. Some scientists wonder whether this layer could slow the great ocean currents that move heat around the planet. Others think the effect will stay small and local. The debate is genuine, and the measurements are difficult because the Arctic is vast and the instruments are few. Villages along these coasts feel the change first. Homes that stood safely for generations now sit a few meters from the edge. Some communities have already moved inland. Others are planning to. The land beneath their feet, once as solid as stone, has become something closer to soft clay. The people who live there describe a kind of quiet grief, watching the shore where their grandparents walked vanish into the waves. From space, satellites trace the retreating coastlines as faint, shifting lines. leaves slumping into milky water, with chunks of black soil drifting out on the tide. From within the soil itself, the change is invisible. Just the slow release of breath that was held since the mammoths walked. Everything here connects. The sun warms the sea. The sea eats the shore. The shore releases the gas. The gas warms the sky. The sky warms the sea again. It is a soft, circular song, playing on a time scale longer than any human life. How loud that song will become, and how quickly, is one of the questions we cannot yet answer. For tonight, it is enough to listen gently from far away. In the great northern forests, the trees have begun to lean. You can see it from the air, in long stretches of spruce and pine that no longer stand straight. They tilt this way and that, leaning into each other, leaning away. Some of them resting their crowns against neighbors that are also tilted. Foresters and biologists have a quiet name for these places. They call them drunken forests. The name is gentle, almost affectionate, but it points to something strange happening underground. For thousands of years, the trees of the far north have grown in soil that sits on top of frozen ground. Their roots cannot push deep because the deep is hard as stone. So the roots spread sideways, weaving a wide, shallow mat just beneath the surface. As long as the frozen layer below stays firm, this mat holds the tree upright. The tree grows tall and slender, reaching for the thin northern light, anchored by a frozen world it never sees. When the permafrost begins to soften, that anchor begins to shift. The ground no longer holds its old shape. In some places it sinks. In others it slumps sideways, sliding gently down a slope that used to be steady. The trees go with it. They lean as the soil leans. They tilt as the soil tilts. A forest that took 2 or 3 centuries to grow can lose its posture in only a few decades. What makes this so quietly remarkable is how slow it is, and yet how fast. On the scale of a human life, a tilting tree seems almost still. You could stand beside it for an afternoon and notice nothing. But on the scale of the forest itself, this is sudden. These woods have been standing more or less the same way since the last ice age ended. The trees of today are the great-great-grandchildren of trees that found their footing when the world was still warming out of deep cold. Their lineage learned to live with frozen ground. Now the ground is changing faster than the lineage can adapt. Some of the leaning trees survive. They keep growing, slowly correcting themselves, bending their trunks back toward the sun. You can find old spruces in the north with curved bases, shaped like the lower part of a question mark, evidence of a ground that moved beneath them when they were young. Other trees do not recover. They fall. They lie across the soft soil, slowly sinking into it, while the mosses and shrubs grow up around them. In time, they vanish into the very layer that betrayed them. There is an open question in all of this, and it is not a small one. Researchers wonder how much of the boreal forest will reshape itself in the coming centuries, and what will grow in its place. Some studies suggest that as the frozen ground thaws, wetter areas will spread, and the slender spruce forests will give way to bogs, sedges, and shallow ponds. Other studies suggest that warmer soils might let new kinds of trees move north, deeper than they have ever grown before. The forest may not disappear so much as trade itself for a different forest. Which of these futures wins out, and where is still being worked out? The trees themselves are part of the story of the ancient air. Their roots stir the soil. Their fallen trunks rot and feed the microbes that wake in the warming ground. When a forest leans and falls, it opens the canopy, lets more sunlight reach the soil, and that sunlight gently warms the layer below. The thaw deepens. More old carbon meets the air, more leaning, more falling. How strong this loop is, and how quickly it can run, remains an unsettled question among the people who study it. Stand for a moment in your mind beside one of these tilted woods. The light is low and pale. The air smells of resin and wet moss. The trees lean at soft angles, like sleepers caught mid-dream, and the ground between them is uneven, dimpled with little hollows where the soil has dropped. Somewhere beneath your feet, ice that has been solid since mammoths walked here is softening, one slow grain at a time. The forest above feels it long before any instrument can measure it. The trees, in their own quiet way, are reading the message of the deep ground, and answering with their bodies. How far this leaning will spread, and how fast, and what new shape the northern world will settle into, are questions no one can yet answer with confidence. The forests are telling us something. We are still learning how to listen. Light moves across the far north in long, slow sweeps. In summer, the sun barely sets, sliding low along the horizon for weeks at a time. In winter, it barely rises, leaving the tundra in a soft blue dusk for months. This strange rhythm of light shapes everything that happens to the frozen ground below. And it may also shape the answer to a question no one can fully answer yet. How fast will the permafrost go? The light that falls on the tundra is not like the light that falls farther south. It arrives at a low angle, skimming across the land instead of pressing straight down. For most of the year, much of that light bounces away. Snow reflects it. White ice reflects it. The pale, dry grasses of the tundra reflect it. Scientists call this bouncing back of light the albedo, a simple word for how bright a surface looks to the sun. A bright surface stays cool. A dark surface drinks the light in and grows warm. Here is where the question of speed begins to take shape. As the permafrost thaws, the surface changes color. White snow gives way to dark, wet soil. Pale lichen gives way to black pools of meltwater. Bright ice gives way to the deep brown of exposed peat. Each of these darker surfaces holds more of the sun's light, and the more light they hold, the warmer they grow. The warmer they grow, the more the ground beneath them softens. No one is sure how strong this effect will be. Some researchers think the change in albedo could speed the thaw far more than the air alone. Others think clouds and shifting, weather patterns may soften the effect, scattering sunlight before it reaches the ground. The evidence is still being gathered, season by season, from satellites and from quiet stations scattered across the north. There is another way light enters the story. When the long summer days arrive, sunlight reaches deep into the shallow ponds that form on the thawing surface. The water glows a soft tea color, stained by the carbon leaching out of the soil below. In that brown light, tiny microbes wake and begin to feed. They break down the old plant matter, releasing gas as they go. some of that work is powered by the sun itself. Light striking the brown water can break carbon molecules apart, a process that may release even more gas than the microbes do on their own. How much and how quickly the sun adds to this release is still an open question. Some studies suggest the effect is small. Others suggest it is larger than anyone expected. The truth may depend on the color of the water, the depth of the pond, and the angle of the summer sun in a given year. The light of autumn brings its own riddle. As the days shorten and the first frost returns, the surface freezes again. But the deep ground does not freeze as quickly as it once did. A warm layer can linger below, releasing gas long after the top has hardened. In some places, researchers have watched the freeze-up take weeks longer than it did a generation ago. That extra time, that extra slow goodbye of summer light, may matter more than anyone first guessed. Winter brings the long darkness. Without the sun, the surface cools. The ice thickens. The land seems to sleep. But under the snow, the ground may still be warmer than it should be, holding the memory of a longer summer. The snow itself acts as a soft blanket, trapping that warmth against the soil. Heavier snowfalls, which some climate models predict for the north, could keep the deep ground from refreezing the way it once did. So the question of speed comes down to a tangle of light and shadow and timing. How much sunlight will reach the darkening surface? How much will be reflected by clouds? How long the warm season will stretch? How thick the winter snow will lie? How deeply the brown summer ponds will glow? Each of these threads has its own theory, its own uncertainty, its own quiet group of researchers watching and waiting. Some models suggest the Great Thaw will unfold slowly, over centuries, giving the world time to understand it. Others suggest the change could come in sudden bursts, in single warm summers that tip whole regions past a point of return. Both ideas rest on real evidence. Neither has been proven. For now, the light keeps moving across the tundra in its long, slow sweeps. It paints the snow gold at dawn and blue at dusk. It warms the dark pools. It lingers a little longer each year. And the answer to how fast this old, frozen world will change is still waiting somewhere inside that light. There is a sound to the thawing north, though most of it is too soft for human ears. It is the sound of a system talking to itself. A whisper passes from soil to air, from air back to soil, and the whisper grows a little louder each time it returns. Scientists call these conversations feedback loops, and they are one of the deepest mysteries in the study of melting permafrost. A feedback loop is a simple idea with complicated results. Something changes. That change causes another change. The second change then pushes the first change to grow stronger. In the frozen north, the warming air thaws the ground. The thawing ground releases gases. Those gases warm the air a little more. The air then thaws more ground. Around and around the whisper goes. If you stood on the tundra in summer and listened closely, you might hear pieces of this loop. The soft pop of a methane bubble breaking the surface of a pond. The faint hiss of gas escaping a crack in the soil. The slow drip of meltwater finding its way downhill. None of these sounds are loud, but together, across millions of square miles, they form a quiet chorus that researchers are only beginning to measure. The trouble is that no one knows exactly how loud this chorus will become. One theory holds that the feedback will be slow and steady. In this view, the permafrost releases its old carbon gradually, over centuries, giving the rest of the planet time to adjust. The thaw spreads, but it spreads at a pace that can be tracked and modeled. The whisper stays a whisper. Another theory worries that the loop could speed up in sudden jumps. Patches of ground might collapse all at once, exposing deep layers of ancient soil to warm air and rain. Lakes might drain overnight as ice walls give way. Microbes might bloom in places that have been sterile for tens of thousands of years, feasting on long-buried plant matter and breathing out gas much faster than expected. In this view, the whisper could rise to something closer to a hum, and then to something louder still. A third possibility sits between the two. The thaw may move slowly in some regions and quickly in others, with no single rhythm across the whole north. Wet ground may behave one way. Dry ground may behave another. Forested permafrost may hold on longer than open tundra, or it may fail more overlap and cancel each other in ways that are hard to predict. What makes these loops so difficult to study is that they connect things that seem unrelated. The brightness of the snow matters because pale snow reflects sunlight while dark soil absorbs it. The depth of summer rain matters because water carries heat down into the ground. The number of shrubs matters because shrubs trap snow and insulate the soil through winter. Even the wandering paths of caribou and reindeer matter because their hooves pack the snow and change how it holds the cold. Every one of these threads pulls on the others. Pull one, and the rest move in ways researchers cannot yet fully trace. A warmer summer might grow more shrubs, which might trap more snow, which might keep the ground warmer in winter, which might thaw more permafrost, which might release more gas, which might warm the next summer a little more, or the shrubs might shade the soil and cool it. The same change can push the system in opposite directions depending on conditions no one has measured yet. There is also the question of how the loops in the north connect to loops elsewhere. Warmer Arctic air may shift the path of storms far to the south. Melting sea ice may change ocean currents that carry heat between continents. Methane released over Siberia drifts on the wind and mixes into air over every country on Earth. The whisper of the tundra is not staying in the tundra. Where it goes next and what it does when it arrives remains an open question. Researchers build computer models to test these loops, feeding in everything they know about soil, air, ice, water, and life. The models disagree. Some show a future where the loops stay gentle. Some show a future where they grow sharp. None of the models can yet capture every detail because the real ground holds surprises that the equations have not yet learned. The scientists know this. They keep building, keep measuring, keep listening to the soft sounds of a system in conversation with itself. For tonight, it is enough to picture that quiet land, whispering in a language we are still learning to understand. There is a quiet kind of mathematics inside a glacier. It is not written down anywhere. It is hidden in the spacing of tiny bubbles, in the slow squeeze of ice over time, in the steady fall of snow that built the glacier flake by flake. Each layer carries a number. Each bubble carries a sample. And when scientists drill down through that ice, they are reading a long, patient equation written by the sky itself. The math begins with snowfall. A glacier is just snow that never melted. Year after year, fresh snow falls on old snow and presses it down. The crystals lose their delicate shapes. They round off. They pack closer. Somewhere around 50 to 100 meters deep, the snow becomes a grainy stage called firn. And in the firn, something quiet and remarkable happens. The little spaces between the grains begin to close. They pinch shut around the air that was there. Each pocket becomes a sealed bubble. Each bubble becomes a tiny museum. The numbers here are gentle and exact. In some places, the air gets sealed in after only a few decades. In colder, drier places, it can take centuries. Scientists must correct for that delay when they read the ice, because the bubble is always a little younger than the ice around it. The math is careful, but it is also beautiful. From a single core, researchers can line up the age of the ice and the age of the air, and read them like two clocks ticking side by side. Then come the layers themselves. Snow falls thicker in some seasons than in others. Dust settles on the surface in spring. Summer sun glazes the top. Winter buries it again. These small differences leave faint bands in the ice, almost like the rings inside a tree. In the upper part of a glacier, those bands can be counted one by one. Deeper down, they thin and stretch as the weight above squeezes them. The math of that squeezing follows simple rules of flow. Ice behaves a little like very slow honey. Given enough time and enough pressure, it spreads sideways and grows thin. Because of this, a layer that was once a meter thick may become a few centimeters thick at great depth. Scientists model the stretching with equations that have been refined over many decades. The work is patient. A core from the deep interior of Antarctica might hold 800,000 years of air in less than 3 kilometers of ice. Each meter near the bottom can carry thousands of years. The numbers compress the way the ice does. What sits inside those bubbles is a kind of arithmetic of the atmosphere, the ratio of certain gases, the faint trace of methane, the the slow rise and fall of carbon dioxide across the long pulses of ice ages and warm ages. When the measurements are placed in order, they form a curve that breathes. It rises. It falls. It rises again. The rhythm is not perfectly regular, but it follows the slow wobble of Earth's orbit, the tilt of its axis, the long stretching and rounding of its path around the sun. These orbital cycles can be predicted to the second, far into the past and far into the future. The sky keeps very good time. Permafrost has its own quieter mathematics, and it is less elegant because it is less ordered. Frozen ground does not lay itself down in tidy layers the way a glacier does. It freezes from the top and from cracks. It traps pockets of old soil and old water, and it sometimes mixes the ages together. Reading the air inside permafrost is harder than reading the air inside ice. One sample may hold gas from many different centuries. The numbers blur. The clock is smudged. This is part of why the glacier cores matter so much to the permafrost question. The cores give a clean baseline, a long, slow record of what the atmosphere used to do on its own. Against that baseline, researchers can compare what is rising from the thawing tundra now. The comparison is not finished. The signal from melting permafrost is still small inside the larger signal of human activity, and untangling the two is an open problem. For tonight, it is enough to picture the math as a kind of music, the bubbles spaced like notes, the layers stacked like measures, the orbits of the planet keeping time underneath. Somewhere in the dark, a drill turns slowly through ancient ice, and a column of frozen air rises into the light. The numbers are waiting inside it, quiet and exact, holding their breath until someone listens. Inside the frozen ground, something quieter than air also waits. Pollen, seeds, tiny grains of plant memory, sealed into the cold soil thousands of years ago. They drifted down through ancient summers, settled into the mud, and then froze in place when winter never quite let go. Each grain holds a record of what once grew here. Each one is a small whisper from a world we did not see. Scientists who study these grains call themselves palynologists, a long word for people who read the story of pollen. They pull cores of frozen earth from the tundra, slice them like a cake, and look at the layers under a microscope. In one layer, they may find the pollen of grasses that grew when mammoths walked nearby. In another, the pollen of small flowers that bloomed in a brief warm summer 10,000 years ago. The frozen ground is a kind of library, and every layer is a page. What makes this so strange is how delicate the whole arrangement is. For pollen to survive across the ages, the soil must stay cold, dry enough, and undisturbed. The ground above must not slump or wash away. The temperature must hover in a narrow band, year after year, century after century. A few degrees of warming and microbes wake up. Water moves. The pages of the library begin to smear. Some of what was written there may simply vanish before anyone gets to read it. Even more remarkable is the question of seeds. A seed is a tiny package of life, wrapped in a hard coat, waiting. Some researchers have wondered whether seeds frozen in permafrost might still be alive after thousands of years. One famous study from a Russian site claimed that scientists revived a small flowering plant from tissue buried for around 30,000 years. The claim is debated. Other researchers wonder if modern roots contaminated the sample. The question remains open. What is clear is that the cold ground is far more biologically active than it looks. Things are not simply dead down there. They are paused. And pauses, like libraries, depend on conditions that are easy to forget. Think for a moment about how thin the margin really is. The Earth sits at a distance from the sun that allows water to be liquid in some places and solid in others. The atmosphere holds just enough warmth to keep the planet from freezing solid, and just enough cold to keep it from cooking. The tilt of the axis brings seasons. The slow wobble of that tilt brings ice ages and warm ages in long, patient rhythms. Inside those rhythms, the high north has held its frozen ground for tens of thousands of years. It works because everything balances. A slightly closer orbit, a slightly thicker blanket of gas, a slightly different mix of ocean currents, and permafrost might never have formed at all. There would be no pollen archive, no seed vaults under the to settle into a state where ice can persist for ages without disappearing. When scientists look at other worlds, they see how rare this kind of balance might be. Mars has frozen ground, yes, but its air is too thin to hold much warmth, and its surface is bombarded by radiation that would shred most seeds. The moons of Jupiter and Saturn hide ice beneath their crusts, but no sunlight reaches their depths. Earth seems to be a place where cold and warmth meet gently, where a seed can sleep through the millennia and perhaps still wake. We do not know how common that is in the universe. We do not know if it has happened anywhere else. So when the permafrost softens, something more than gas escapes. A kind of memory escapes too. Pollen that recorded long-lost forests begins to break down. Seeds that might have been viable lose their cold protection. The ancient summers preserved in those layers blur into one another. Researchers are racing in a calm and patient way to read what they can before the pages turn to mud. They take cores, they map sites, they store frozen samples in laboratories far from the tundra. They are trying to copy the library before the library is gone. Whether any of those seeds could truly grow again, whether any of that pollen still carries genetic information that surprises us, is part of the open question this section sits with tonight. The frozen ground remembers. We are only beginning to learn how to listen, and we do not yet know how much time the listening will take. Far above the tree line, in villages that have stood for many generations, people have been watching the ground for as long as anyone can remember. They know the land in ways that no satellite can match. They know which slopes hold their shape through summer. They know which lakes freeze first and which thaw last. They know the smell of the earth when it is healthy and the smell of it when something has changed. In recent decades, these northern communities have noticed things that puzzle them. The ground rises and falls in new patterns. Hunting trails that families have used for generations now sink underfoot. Cellars dug into the permafrost, used for storing food through the long winters, have begun to flood. Some of these cellars held meat safely for over 100 years. Now the walls weep, and the floors soften, and the cold that once felt eternal is slipping away. Scientists who study the far north have started to listen to these observations more carefully. The reason is simple. The people who live on this land have a record that no instrument can replicate. They remember what the river looked like when their grandfather was young. They remember where the caribou used to cross. They remember the shape of the shoreline before the waves began taking it back. This kind of memory stretches across generations, and it captures slow changes that short scientific studies might miss. Still, even with both kinds of knowledge combined, much remains unclear. One open question is how quickly local change matches the broader pattern across the Arctic. Some villages report thawing that seems faster than nearby regions. Others sit on ground that has held firm while neighboring valleys collapse. Why does the permafrost give way in one place and stay strong in another only a few miles off? The answer likely involves soil type, ice content, vegetation, and water flow. But the full picture is still being assembled, one careful measurement at a time. Another mystery involves the sounds people describe. Elders in some communities speak of new noises in the land. Small cracks, sudden settling, a kind of sighing as the ground shifts. Researchers are only beginning to study these acoustic signals, and it is not yet clear how they connect to deeper changes below. One idea is that the sounds mark ice lenses breaking inside the soil. Another is that gas pockets are venting through small openings. Both ideas may be partly right. Neither is fully proven. The question of what lies hidden in the frozen ground also remains wide open. Northern peoples have long known that the permafrost holds bones, tools, and remnants of older worlds. As the ground softens, more of these objects rise into view. Some are bones of animals that vanished long ago. Some are wooden artifacts preserved by the cold. Each find raises new questions about who lived here when they lived, and how they moved across the land. The frozen earth has been a quiet archive, and that archive is beginning to open faster than anyone can read it. There is also a deeper uncertainty about what the thaw means for daily life in the decades ahead. Houses built on permafrost rely on the ground staying solid. When it softens, foundations tilt, roads buckle, pipelines flex in ways their builders did not plan for. Communities are now asking how to adapt, and the answers are not simple. Some villages have begun to move. Others are reinforcing what they have. No one knows yet which approach will hold up best, because the ground itself is still changing in ways that have never been observed before. What scientists find most striking is how much the northern peoples have already taught them. The idea that permafrost was a single, uniform layer has given way to a much richer picture, partly because local hunters and herders described variations that instruments later confirmed. The role of snow cover in protecting or warming. The ground became clearer through traditional knowledge of where snow gathers and where wind sweeps it away. Even the timing of the thaw, season by season, has been refined by people who watch the land every day. So a different kind of mystery sits at the heart of this story. It is not only about chemistry or physics or buried gases. It is about how two ways of knowing the world can come together and what they might reveal when they do. The northern peoples are watching. The scientists are listening, and the ground beneath them all is shifting in ways that neither group can yet fully explain. The question of what comes next belongs to both, and the answer is still being written slowly in the soft soil of a warming north. High above the frozen ground, a quiet fleet of machines drifts in slow circles around the Earth. They are satellites, and they have become our patient watchers of the permafrost. They cannot feel the cold. They cannot smell the strange breath rising from the thawing soil. But they can see things our eyes never could, and they can listen in ways the old explorers could only dream of. Some of these satellites carry instruments that measure tiny shifts in the height of the ground. When permafrost thaws, the soil sags. It sinks by a few centimeters in some places, by whole meters in others. From hundreds of kilometers above, the satellites notice these dips. They draw slow maps of where the Earth is settling, like an artist sketching a sleeping body, breathing in and out over the years. Other satellites watch for gas. They scan the air for the faint signature of methane and carbon dioxide, the two breaths the permafrost lets out as it warms. The instruments work by reading sunlight. Each gas absorbs certain colors in its own particular way, leaving a kind of fingerprint in the light. By studying that fingerprint, the satellite can guess how much gas is rising from a stretch of tundra below. It is a gentle form of listening, done with light instead of sound. Yet even with all this watching, the picture stays blurry. The Arctic is enormous. Cloud cover hides huge regions for weeks at a time. Snow reflects light in confusing ways. The satellites give us hints, not certainties. Some researchers think the permafrost is releasing more gas than the satellites can see, because much of it seeps out in small, scattered plumes too thin to register from space. Others think the satellites overestimate the loss, because nature pulls some of the gas back down into wetlands and forests. We are still learning to measure. The truth lives somewhere between these views, and we do not yet know exactly where. Now imagine these same satellites 1,000,000 years from now. They will be long gone, of course. Metal and glass cannot last that long in the harsh weather of low orbit. Most will have fallen back to Earth as tiny meteors, burning into nothing. A few might have drifted into higher orbits, frozen and silent, ghost ships circling a planet that no longer remembers them. The permafrost itself, in many places, will also be gone. In its place, there may be wet bogs, or grasslands, or forests of trees we cannot yet picture. New layers of frozen ground may form again in places we now think of as warm. The Earth is patient. It has frozen and thawed many times already. Push further out to 1 billion years. The sun will be brighter and hotter than it is today. Some studies suggest the oceans may begin to evaporate by then, slowly, over many millions of years. Permafrost, as we know, it might no longer exist anywhere on the surface. The frozen secrets we worry about now, the ancient air, the sleeping microbes, the bones of long-vanished animals, will have been released, broken down, or carried into the wider atmosphere. Whatever stories they held will have dissolved into the chemistry of a hotter world. And further still, in a few billion years, the sun will swell into a red giant. The Earth may be swallowed, or it may be pushed outward into a new orbit, scorched and bare. The continents we know will have crashed and split many times over. reindeer trails. No villages near the coast. The whole frozen north, with all its mysteries, will exist only in the memory of light. The faint signals are satellites once beamed outward into space. Some of those radio whispers are already traveling beyond the solar system. They are the last echoes of our patient watching. New things will rise in place of what is lost. New worlds form around new stars. Somewhere out there, perhaps, another planet is freezing for the first time, growing its own thin skin of permafrost over young soil. Air is becoming trapped in its bubbles. A long story is just beginning, like ours did once. The universe seems to enjoy repeating its quiet patterns, with small differences each time. For now, the satellites keep watching. They drift overhead in the dark, gathering numbers, painting slow maps of a changing land. The full meaning of what they see is still beyond us. We are gathering pieces of a puzzle whose shape we cannot yet make out. Tonight, the watching continues, soft and steady, while the ground below breathes its old, slow breath into a sky full of careful, listening eyes. Step back for a moment. Step back from the tundra and the slow rivers, from the slumping coastlines and the lakes that hiss in summer. Step back from the frozen soil and the bones inside it. Look at this whole quiet question from as far away as you can, from the place where the earth is only a pale blue dot turning in the dark. From out there, the permafrost is a thin rind on a small world, a skin of frozen breath wrapped around the top of a planet, which itself orbits one ordinary star in one ordinary arm of one ordinary galaxy among hundreds of billions. And yet inside that thin rind, the planet has been keeping notes. Notes about what the air tasted like during the long cold. Notes about which microbes were alive and which forests grew, and how the world breathed in and out across thousands of slow years. The theories that compete here are not just about ice. They are about how a planet remembers itself. Some researchers think the thaw will be gradual, a slow exhale spread across centuries, giving the earth time to adjust and absorb. Others wonder if the release will come in pulses, in sudden collapses of ground that send old gases up in great quiet bursts. A third group thinks the answer lies somewhere between, with different regions thawing in different ways, each on its own schedule. The data is incomplete. The models do not yet agree. The question remains open, and underneath those competing theories is a stranger thought. Every atom in that frozen ground was born somewhere else. The carbon in the old plant matter, the nitrogen in the trapped bubbles, the iron in the bones of mammoths sleeping beneath the moss. All of it was forged in stars. The calcium that once made a tusk was cooked inside a sun that died before our sun was born. The oxygen in the ice came from generations of stars that lived and burned and scattered themselves across the dark. When permafrost releases its ancient air, it is releasing atoms that have already lived many lives. You are made of the same material. The water in your body has been rain, and ocean, and snow, and maybe once, long ago, a bubble inside a glacier. The carbon in your hands has been forest, and coal, and breath, and stone. We are not separate from the frozen ground. We are another arrangement of the same old atoms, briefly walking around, briefly wondering about ourselves. That is part of why this mystery matters in a way that is hard to put into words. The permafrost is not only a climate puzzle, it is a record of how a living world stores its own memory. And we are trying to read that record while it changes in our hands. Some scientists believe we will learn enough in time to understand what is coming. Others suspect that some of the answers will only arrive after the archive is gone. Both views are held by careful people looking at the same evidence out at the edge of the solar system, on moons like Triton and Pluto, and the cold worlds beyond. There are other kinds of frozen ground: nitrogen ice, methane ice, ancient surfaces that have never known a thaw. Studying our own permafrost may help us understand those distant places. And studying those distant places may help us understand our own. The universe keeps offering us mirrors if we are patient enough to look. There is something almost tender about a planet that holds its breath for so long. The Ice Age ended more than 10,000 years ago, and still, in pockets deep below the moss, the air of that older world has been waiting through the rise of every civilization, wading through every war and every harvest and every song ever sung. The ground did not know we were here. It simply kept the bubbles safe. Now those bubbles are beginning to find their way back into the sky. The carbon will join the carbon. The methane will join the methane. The atoms will move on, as atoms always do, to become something else. A cloud, a leaf, a breath, a bone. The cycle is older than us and will continue long after us. And that is not a sad thought. It is only a true one. Tonight, somewhere on the quiet curve of the north, a small bubble is rising through black water under a pale sky. It has been waiting a very long time to come home. And we, made of stars and water and time, are here to wonder about it. Picture for a moment the far north as it is right now, in this very hour. A wide plain of soft tundra stretches under a low sun, its mosses brushed with frost. A river winds slowly through it, dark and patient, carrying meltwater toward a sea that has known this same coast for 10,000 years. The wind moves, but quietly. The ground beneath, in most places, still holds. Snow drifts settle into shallow hollows. A single fox crosses a ridge and vanishes into the pale light. This is the world we have been wondering about together tonight. A world of frozen soil and ancient air. A world where bubbles of breath from the Ice Age lie sealed inside the ground, waiting in a silence older than any city. We have walked in our imagination across Yedoma cliffs and quiet lakes. We have listened for the small pop of methane rising through still water. We have stood at the edge of soft craters that opened without warning. And we have looked at mammoth bones lifting slowly out of the mud as the seasons turn. And through it all, the central question has stayed open. We do not yet know how fast the permafrost will release what it holds. We do not know how much carbon will wake, how many microbes will stir, how the feedback loops will tight or loosen in the decades ahead. Some researchers believe the thaw will be gradual and uneven. Others wonder if certain regions could shift more quickly than the models suggest. The evidence is still gathering. The answers are still forming. The ground itself is still speaking, slowly, in a language we are only beginning to read. There is something gentle in sitting with a question this large The permafrost does not need us to solve it tonight. The satellites will keep listening. The scientists will keep measuring. The northern peoples will keep watching the rivers and the ice as they always have. And the planet will keep turning as it has turned for more than 4 billion years, carrying its frozen memories through the long dark of space. Step back now in your mind and let the view widen. See the curve of the earth from far above. See the white crown of the Arctic, the green and brown belts of the forests, the blue of the seas. See the soft glow of cities on the night side, like scattered embers. See the thin shell of air that holds all of it, fragile and bright against the black. From this distance, the planet looks calm. It looks whole. It looks like something worth resting beside. Pull back farther. The earth becomes a small blue point. The moon drifts nearby, pale and patient. The sun burns steadily in the middle distance. Beyond, the other planets trace their slow, quiet orbits, each one carrying its own mysteries, its own frozen surfaces and hidden oceans and unanswered questions. Pull back farther still. The solar system becomes a tiny bright cluster in one arm of the galaxy. The galaxy itself turns slowly, a great wheel of stars, and beyond it, more galaxies than anyone can count. You are part of all of this. The breath in your chest right now is made of atoms forged inside ancient stars. The water in your body has cycled through clouds and rivers and seas for billions of years. The same physics that shapes the permafrost shapes you. The same long patience that holds the ice age air in frozen soil holds the night around you now. There is no urgency in any of it. The universe is in no hurry. The galaxies turn. The stars burn. The permafrost waits and changes and waits again. And here, in this quiet room, you are small and held, a single warm thread inside something unimaginably vast and unimaginably gentle. Let your thoughts soften now. Let the questions stay open. They will still be there in the morning, and the morning after that, and the world will keep wondering with you. The frozen ground will keep its slow conversation with the sky. The microbes will keep dreaming their 1,000-year dreams. The mammoth bones will keep rising, gentle as memory, into the light. Rest now. The planet is spinning, slow and steady beneath a sky full of stars. The old air is still mostly sleeping in the ground. The mystery is still ours to wonder about together for many nights to come. Subscribe for a brand new space topic every night. One tap and something incredible is waiting for you tomorrow. Sweet dreams.